Imagine you're at a huge party. At the start of the night, your friends are spread all over the place. Some are by the snacks, others are on the dance floor, a few are outside. But as the evening goes on, something interesting happens. Your group of friends starts to gather. First, they're all in the same room. Then, they're all in one corner of that room. As the hours tick by, they get closer and closer, huddling into a tight little circle. This is a bit like a special type of sequence in mathematics. We call it a Cauchy sequence. It's a list of numbers that over time behave just like those friends. At first, the numbers might be far apart. 10 minus 5, 50. They seem to be going nowhere in particular. But a Cauchy sequence has a special rule. After a certain point, all the numbers that come after it start to get incredibly close to each other. They begin to cluster. Eventually, any two terms from far down the line are practically indistinguishable. They're all sticking together. Let's make this idea a bit more precise. The rule for a Cauchy sequence is beautifully simple. You can name any small distance you like, no matter how tiny. Let's call it your challenge distance. 0.1, 0.001. A number with a million zeros after the decimal point. Any size. If a sequence is Cauchy, I can find a point in the list after which every later term stays within your chosen distance. They're trapped in a tiny bubble. It's a guarantee. Think of it as a game of squeezing. You set the rules and the sequence meets them. Ignore the early terms. After some n, all later numbers stay within the tiny interval. Come back with an even smaller challenge, and they will meet it further down the list. This is about the sequence's internal behavior. Relationships between terms. Not checking an external finish line, like 0 or 7. If they come down into the same tiny neighborhood, we call the sequence Cauchy, predictable, unreliable. So these sequences of numbers are getting cosier and cosier. It feels like they must be closing in on a specific number. But is that always guaranteed? What if they were closing in on a whole? If our number line only had rationals, you could create a sequence getting closer and closer to 2. But 2 isn't rational. There'd be a gap. 114, 141, 144, and so on. The terms get closer, but their target isn't rational. It's a gap. This is where the real numbers come to the rescue. The real numbers are a complete space, no gaps. Every point a sequence could head toward exists on the real line. Numbers like P and 2 are irrational. They plug the holes. Rationals plus irrationals form a smooth, continuous line. Completeness is the crucial link. For reals, any Cauchy sequence is guaranteed to find a home. The numbers can't cluster toward a non-existent point. Every possible landing spot is already there. That's what makes calculus and analysis work. So why do mathematicians get excited? It's all about certainty. We love guarantees. Every Cauchy sequence of real numbers converges. That fact is a powerful tool. It lets us prove a limit exists without knowing the value ahead of time. We just check whether the sequence's terms get closer to each other. If they do, we know they'll land somewhere. This helps in practice. For example, to compute P, a program might produce 3.1, 314, 3141, 34059, and so on. How does it know when to stop? Cauchy behavior gives confidence. The approximations aren't wandering. Each step closer to previous ones shows stability. This is foundational to real analysis. Limits, derivatives, area calculations, and numerical methods all rely on sequences that behave predictably. V-completeness acts like a safety net. No Cauchy sequence is left wandering. The sequence's stability guarantees a destination. Even endless lists can settle down. Cauchy sequences give order and predictability to the infinite.